We complete the square. We take x, we add, look at the 4. What's half of 4? 2. So we do x plus 2 quantity squared. All right. Now, what is this? If you look at this, if you multiply this out, you've got yourself an x squared plus a 4x plus a 4. So I have to subtract 4 to be fair. So what I'm saying is, if you want to understand why we're doing what we're doing, it's just that these first two terms are identically equal to that square minus that number. It's just a way of grouping the linear term in x into a square. And why is that nice? Because this gets you to x plus 2 squared plus 1. And here's the theorem. If after you complete the square, you're left with the square plus a number, that means that it's a prime polynomial. This means the polynomial is prime, which means it cannot be factored with real numbers. If we had complex numbers, we could factor it. All right? And I'll talk more about that another day. Let's do another example. How about x squared plus 4x minus 5? Complete the square. Pretty much the same, right? What's the difference, though? When we complete the square on that one, with that just simple difference of plus to minus, after we complete the square, we get x plus 2 quantity squared minus 9. So if after you complete the square, you get minus a number, this minus right here means we can factor over R. More than that, how do we factor over R? What is this? Yeah.
Why can we factor?
Oh, I'm showing that. Good question. How about this? This 9 is 3 squared, right? Right? It's 3 squared. What are we looking at? What is this? This is a squared minus b squared. It's a difference of squares. So this is x plus 2 plus 3 times x plus 2 minus 3. What is that, though? That is x plus 5 times x minus 1. Did I mention that math is not postmodern? Like, I can't have my truth and you have your truth. There's just the truth, right? And one of the truths of mathematics is that the factorization of a polynomial is unique up to reordering of the factors. So if I start with x squared plus 4x minus 5, in one of the examples it factors to x minus 1 times x plus 5, it also factors over here to x plus 5 times x minus 1. See that you can switch the order, but it's the same answer. What's the difference, though? You're like, well, you did, the second way you did was confusing and new, and I don't want to learn it, right? I mean, I know I'm fighting you on this. Do you understand the difference, though? I didn't do any guessing here. I follow this pattern. I take half of the middle, I square it, I subtract it, and then I use the difference of squares formula. That factors it every time. Even when the numbers are ugly, really ugly. For example, So give me numbers, any numbers. I'll start out. X squared. What do you want the middle one to be? 8x. All right. Well, that was nice. Thank you. What example are we on? I keep losing track. Are we 14? 14. What's the question? How about plus 1? Can you factor this? You definitely cannot factor it using previous course mathematics, right? This is new. This is college algebra. We didn't know how to factor this before, probably. But I can with completing the square. Let me show you. So half of 8 is 4. What's the next thing? To be fair, we have to subtract the square of whatever we added. So subtract 4 squared, which is 16, plus 1. What is that? Well, that is x plus 4 squared minus 15. And here, let me just show you a quick trick. Watch this. We just square root squared. Any positive number you can replace with, like, you know, what number squares to 13? Well, 13 is equal to the square root of 13 squared. What do you know? I mean, this is just a dumb identity, but it's helpful to us because now we have a squared minus b squared. So that's the pattern. So we do x plus 4 plus the square root of 15, x plus 4 minus the square root of 15, factored. So I refer to this process as factoring via completing the square. Did I mention that you don't need to guess, that it's just step by step? Now, is it as fast as what we started with? Certainly not. When you can factor with nice whole numbers, well then do that, right? You can fall back on this method for nice problems. But if it's ugly, and it doesn't work out on the board, right? Please consider using my method, okay? It's not my method. I mean, I'm sure I don't know who defined this to start with. Let's see here, another example. Let's see here. Let's work one with a fraction, yeah? So x squared plus 3x plus 5. So this one's annoying because we can't help but work with fractions. So what's half of 3? 1.5, yeah. Or we could write x plus 3 halves, right? We square that. I have to subtract the square of the thing I added. That's the completing the square step. So minus 3 halves squared, and then plus 5. And you know, the bad news here, in some sense, is that you got to do some fraction adding, right? So let me do it off over here. 3 halves squared is what? 3 halves squared is 9 over 4. 9 over 4 plus 5 is 9 over 4 plus, I think, 20 over 4, right? So what we're really looking at here is x plus 3 halves squared minus 29 over 4. Wait a minute. My bad. What did I do? Is it plus? The minus is with the 9/4, right? I got to pay attention, yeah? So we've got minus 9/4 plus, which gives me what? 11/4, right? So this actually is not, it works out to plus 11 over 4, yeah? And this shows me what? So thus, you know, this is prime. It's a prime polynomial. You cannot factor it over the real numbers. So I hope now that I've showed you this, you can make sense of, like, in the homework, right? In like problem Problem 15, I'm just asking you to do the same for ABC, right? So you can hopefully, and like problem 15, problem 16, problem 17, you should try to do these this weekend to prepare for the quiz Monday. Wait a minute, Monday? Tuesday, yeah. Again, if you got questions about your quiz, you can ask me. It's all good.